Hello, everyone. Hope you're doing well. We are going to finish up this kind of subunit here for our Intro to Classical Analysis by finishing up talking about some properties of our metric spaces. Next week, the first thing that we're going to do is take a look at all of these properties that we've gathered up and start seeing how these things start tying into something that we have been kind of building up to, which is an application of all of this metric space material in terms of solving partial differential equations using things like Fourier series and so on and so forth. We'll get to some of that stuff at the beginning of next week. For this week, we're still kind of focusing on getting a handle on metric spaces, knowing what all kinds of properties that we could use to start visualizing these. Today, you can see we're talking about a property called compactness, which is going to help us get to a version of the extreme value theorem that we talked about last time, or rather back in week 2, in terms of the real numbers. And we would like to start getting to taking all of these properties, and once they all combine together, know a good bit about, okay, we can make our way around metric spaces. Maybe now we can start working on some very rigorous and sometimes detailed arguments that get us to some very important results and theorems in this sort of realm. We're still kind of getting our sea legs though, and that's exactly what we're doing this week, is finishing up that process of knowing how to be working through the world of a metric space in a way that it seems to kind of want us to go toward, especially when it comes to compactness. We'll see how this is kind of a topological version of finiteness. You remember how we've defined a topology as a collection of open sets that are a subset of the power set of a particular space that we live on. So topology usually is something that has to deal with open and closed sets. But there's also some other things that are interesting here with topology. We'll talk about today how the notion of a compact set is something that helps us in this world of topology. We'll give an example here in just a little bit. But a notion of something that is also very related to topology that we saw last week is that a continuous, or continuity, maybe better to say, continuity here is a very topological notion, because it doesn't really have much to do with the notion of needing a particular epsilon and delta ball like we saw in our final formulation of continuity when we visited it on the second video lecture of last week. Instead, we said that all that really has to happen is that open sets have inverse images that are also open. Or, as an equivalent notion, closed sets map back to closed sets when mapped through an inverse image of a function. That was all it needed for the function to be continuous. This seems to take our notion of that we initially had for continuity, which is very tied to the metric here, and just puts it into the metric topology of that space, just the notion of open and closed sets in terms of that. Gratefully, we were able to see a very strong tie between those to kind of make that make this something that made sense. We started with epsilon and delta and then realized that these were neighborhoods of particular points. And then eventually you could even say you can take the center away from what these open and closed sets were. You could just make them any open set or any closed set in our image and map that back into our domain. So continuity is a very topological notion in the sense that it deals with open and closed sets. And so we're going to see that compactness, being another topological notion here, is going to connect very neatly with continuity. Let's see an example of this in terms of the real numbers. Now, this theorem here is something that we can probably get a handle on very quickly, which is that if you have a set that is a finite cardinality, let's call it E, like we have here in this theorem, and F is bounded on each X value inside of the set E, well, F is going to be globally bounded on the set E. When I say globally bounded, I mean that it is bounded by a single number on the entire set, right? So I'm basically saying that for all X inside of E, or rather there exists an M value, and we can put this just as a real number, such that for all X in E, the absolute value of f of X is less than or equal to M. This is what I mean by the sense of globally bounded. It's saying that the function has a maximum and a minimum on its entire set, kind of like how we saw with the extreme value theorem back in week 2. The proof of this is you have a finite set, so you can just put all of your elements into a finite list, and you know that each absolute value of f of xi is less than or equal to m sub I for each individual point x, and that's because f is bounded on each individual point. Well, if you just take the value that is the maximum of each of those individual bounds, then for all x values inside of E, f of x has to be inside of this closed interval from negative m to m. So f has to be bounded on the set E. Now, this particular theorem doesn't seem to tell us something very strong. This is something that probably would make sense if we just kind of said it, right? If you take the endpoints and you have the first point is bounded between -1 and 1, the second point between -2 and 2, it makes sense that your last point being bounded by, say, -n to n, that bound would work for any single point inside of your finite set. But we do seem to require finiteness on this. If we had tried to generalize this to an infinite set, it doesn't seem like this sort of thing would work. If I just said if E is infinite and then tried to say the same theorem, I see no reason for this to be true, right? You could say, okay, well, I'm going to take the set 0 to infinity, and I'm going to take a look at f of x equals x squared, for example. This function is going to be bounded on each and every single point that I might choose. In fact, the function f is just whatever that value is at each and every point. But it is definitely not globally bounded. It goes off toward infinity. So this kind of gives us a little non-example in the infinite case. So we need to say how we can make this stronger. What can we do here instead of saying just E is infinite? Is there a notion that is maybe a good replacement for E being finite? Well, if the function f is just bounded on each x and e, then that's not enough. We would need to add something more to the function f to make that work. But gratefully, we're not typically just concerned with arbitrary functions. We usually want our functions to have a level of niceness to them. Oftentimes, we ask them to be maybe this definition of locally bounded. We could say a function f is locally bounded on a set E if for all x and e, there exists a delta greater than 0 so that f is bounded on the open interval centered at x of radius delta. As an example, continuous functions satisfy this definition. You can think about y, perhaps, starting this through the epsilon delta definition. Here, you can just let your epsilon be equal to 1, for example. Well, then you're going to be able to find a delta so that f is bounded on that interval because it's in between 1 of its function value at x. So continuous functions are an example of locally bounded sets. And usually what we want to do is deal with continuous functions in this world. Sometimes maybe they have little breaks in them, little maybe jump discontinuities. They're piecewise continuous instead, but we could probably generalize some of our theorems here to piecewise continuous functions as well, depending on how many pieces they are in. But with this added strength, we can relax our condition E to be closed and bounded. We can now write a theorem that says, let E be a closed and bounded set. Then every function f from E to R that is locally bounded on E is globally bounded on E. So notice that once we strengthened our function a little bit, we were able to generalize our set E to be a type of infinite set. This infinite set that we're dealing with, it has only topological conditions on it. 1, it has to be closed. 2, it has to be bounded. That just means that there exists some m that is inside of some sort of particular maybe closed interval or open or finite interval, finite length interval, I should say. Then the function f that is locally bounded or perhaps continuous, then again, another topological condition, is something that can be said to be globally bounded on E. By the way, notice that this particular theorem is the extreme value theorem. We've just generalized it slightly from the notion of continuous. To say something is globally bounded on E means that it's going to have a supremum and an infimum. And we've talked about how combining this with Bolzano-Weierstrass in terms of the real numbers there gives us a particular point that we could be converging towards. So this is very close to the extreme value theorem. The only thing is that Bolzano-Weierstrass needed a completeness condition on our set, and we don't necessarily have this if we just have closed and bounded. So we don't necessarily have the full strength on that, but we do have a very strong, a very close version, a neighboring version of the extreme value theorem here with this theorem. So knowing that we can get this close with stuff like this tells us, okay, maybe we can actually get to the extreme value theorem in terms of metric spaces. if we are looking at particularly closed and bounded sets. Now, there's an interesting thing here is that we can define closed and bounded as something not just on the real numbers. We could be defining this on any metric space. So we could define, for example, let's say that you have a metric space X and D, then we can say a set E, a subset of X, is bounded. And I think we've done this before, if its diameter, which is the supremum for all of over all X and Y, and the distance for all X and Y inside of the set E, if this supremum is finite. So this is how we could say a set is bounded, in which case we can now work on bounded in terms of just being instead of set inside of a finite interval. We could say that this is just a particular place where if you take any two distance points, you know it's going to be bounded by a particular supremum, and that supremum is finite. So that gives us a closed and a bounded set. So for example, the interval 0 to infinity would not work in terms of this definition. And that's because if I try and take the supremum over all possible distances in that set, I could get points at distance 1, 2, 3, 4, however large I want them to be. So the supremum would have to be infinite. So let's revisit then this notion of Bolzano-Weierstrass. This seems to be kind of the missing link that we need in order to get that version of the extreme value theorem that we're looking toward. Let's first make a definition that kind of is going to be helpful for us here, and we'll start making some generalizations here for terms of the real numbers. Let's define this. We say a set E is compact if every sequence S of n in the set E has a subsequence that converges to a point in E. Notice that compactness is a little bit different than closed. Closed says if you have a sequence S of n that converges to a point S, if it has, like, for example, to like a boundary point or something like that, then that limit of the sequence is inside of the point E. This one asks us to do something different. This says every sequence in E has a subsequence that converges to a point in E. So any sequence, not even just a convergent one, has a subsequence that converges. To give an example, let's say that you took the set, maybe the one that we were looking at from before, this now being the closed interval going from 0 to infinity. Notice that we would call this a closed set in terms of the real numbers. Its complement is certainly open, for example. If I take this set, I can now construct a sequence 1, 2, 3, 4, just the sequence of the natural numbers, and such that any subsequence that I choose out of the natural numbers does not converge in the relative metric from that it gets from the real numbers. So this has no convergent subsequences in the relative metric on R. So this is an example of a closed set that is not compact. So this is not a compact set because I have found a sequence that any subsequence that I might choose cannot converge. It certainly is not even Cauchy. But of course, anything that is not closed also cannot satisfy this condition. 0, 1 is also not going to be compact if I make it closed on 0 and open at 1, for example, because now I can take a sequence like 1 minus 1 over n, and I can look at this sequence and I can find subsequences that converge, but any subsequence of 1 minus 1 over n would have to converge to the limit of the entire sequence, which is 1, which is not inside the set. So these are examples of non-compact sets. 0, 1 would not be an example, and as would 0 to infinity. So there seems to be this kind of combination that we need for this set. Not only does it need to be closed, it also needs to not have this ability to go off toward infinity. It likely needs to be bounded. Here is that notion of boundedness that we have from before. So that's the same definition as given previously. This m value is the stand-in for the supremum of all such distances. So let's go ahead and see this theorem. You may be familiar with this as the Heine-Borel theorem from an advanced calculus course, but this tells us that we can characterize compactness by exactly these two conditions whenever you're inside of the set Rn. So you can say if you have a subset in Rn, then E is compact if and only if E is closed and bounded. This is exactly another way of formulating this notion of compactness. That is, the subsequential definition, something in terms of sequences, can be given something completely topological. as it can, after rearranging its terms and how we express it. So this theorem says that we can write compactness instead of in terms of sequences. We can write it as a completely topological notion in terms of open and closed sets. At least that's how we've been using it in this class. So let's take a look here at this proof. First, let's show that a closed and bounded set is going to be compact. So start with something that is closed and bounded. So x of n is a sequence contained in E. Since we're in Rn, we know Bolzano-Weierstrass is a valid theorem here. So we know that it has a convergent subsequence. Let's call it like x of n sub k. Well, if it converges to x, then x is going to be inside of E because E is closed. And we just need to combine those two things together. The boundedness plus Bolzano-Weierstrass gives us a convergent subsequence. And then we have that x is in E because the set E is closed. That gives us one direction of this Heine-Borel theorem. And this other direction says, okay, well, let's say that you have the set E with the property that every sequence has a subsequence at a point in E, that it converges to a point in E. Then we're going to go through and say that such a set would have to be closed, and it would also have to be bounded. So that's exactly what we're going to try and do. So starting with E being bounded. If E is unbounded, then we can choose a sequence that diverges to plus or minus infinity, and no subsequence of that sequence can even converge. It's kind of like our example with the 0 to infinity. If you have something that is unbounded, then that means that you can continue to make the distances between your points larger and larger as you go through them. You can always pick a distance of 0.1 and 0.2 or 0.3 farthest away from any of the other points that you have, in which case you can make this sort of argument. It turns out that E is also closed. Well, if it's not, then it has a boundary point Z not inside of E by definition, and you might be knowing where this sort of thing is going. We can then find, because E is a boundary point of this set, we can find a sequence that converges to it. Any subsequence that you might choose would have to converge to that point, but that point is no longer in the set. Therefore, it could not be compact. So this is basically using these two kinds of examples to our advantage to say that any compact set must be closed and bounded. Notice now that the extreme value theorem statement can now be saying, because we asked for our functions to be on a closed and bounded interval from A to B, we could have now just said a compact interval. Any interval that is compact, it's any interval that is closed and bounded. So this notion of compact seems to be very connected to statements like the extreme value theorem. And things like this are going to be necessary for us moving forward with metric spaces so that we can be working and showing the similar things that we have been showing in the real numbers, showing them in terms of metric spaces. This is kind of one of our little sub-goals here with introducing metric spaces at all, is to say, do these things look like the real numbers, or how do they change? What's different if I now replace a metric space of Rn with a metric space of the continuous functions? Do I have to do something different now that my world looks a little bit stranger? Like it's harder to work with these functions, a bit more unwieldy than it is with just numerical vectors. So let's take a look here at how we could take this Heine-Borel theorem, which was only for Rn, notably, because that we needed two things that are not possible or we had not yet proven for metric spaces. One of those things is we mentioned a sequence diverging to plus or minus infinity. In terms of Rn, what that means is that you have this sense of being able to keep pushing your points all the way out toward the infinite realm of that function. But we don't have these axes here when we're looking at metric spaces. We don't have this notion of diverging to plus or minus infinity. So in a generic metric space, this may not make sense. What we're going to have to do is replace this notion with unboundedness. In fact, I think that maybe what we ended up trying to do here is that if you have something that is unbounded, then you could probably just say, okay, well, then maybe I could think of an unbounded set in terms of a metric space and start working with it in terms of that. And in fact, that's exactly what we're going to do here in this lemma, is to say that we're going to show that we can just replace sequences that diverge to infinity or negative infinity, kind of like in our 0 to infinity example. We're going to now replace them with just unbounded sets and show that these sorts of things still work. The other point is going to be a little bit trickier, which is that if we needed to show that a closed and bounded set was actually compact, we needed to use Bolzano-Weierstrass. This was the theorem that tells us that we can get a convergent subsequence out of all of this in order to get this compactness. But we've only proved that for Rn. We have not proved that for a general metric space. So that's not something that we can immediately do. So we have a couple of options there. We either need to reprove Bolzano-Weierstrass, or excuse me, or we need to come up with a different way to come about this other sort of direction. Certainly, with going from right to left, we could say compact sets are closed and bounded, but perhaps going the opposite direction, we need to say something more. We'll see if we need to get to that point once we get to the later half of this particular video lecture. For now, let's go ahead and replace this notion of sequences diverging to plus or minus infinity with this notion of unboundedness. So first dilemma, every unbounded set in a metric space contains a sequence with no convergent subsequence. Okay, so basically if we negate the definition of bounded, this only gives us that there are sequences A sub m and B sub m such that the distance between those two sequences, or any corresponding elements between those two sequences, is greater than m for all m in the natural numbers. This is what we get from negating that definition of bounded. And that's a little bit unwieldy for us because I'm asking for one sequence that has a no convergent subsequence. And how am I supposed to know if A sub m and B sub m does the job? Well, let's simplify things down by trying to boil things down to one sequence here with this particular proof. We first show that if there exists a point C in this metric space X such that the distance from A to C is less than or equal to M for all values inside of our set. I have changed the name of my set. I need to change it back to X. So this needs to be X here. Let me go ahead and make these changes real quick while I talk about this. If we have some sort of centralized point here inside of our set, let's say that that centralized point here is something like A. If I have there exists a centralized point that any other point is less than or equal to M from, then I'm going to say that my set is bounded. Basically, where this is going to come from is the triangle inequality. If I have one point that can reach to the farthest edge here and the farthest edge here, then the farthest that these 2 points can be apart is based off of the triangle that would be formed if I form that sort of space. And that's exactly what we have right here. The distance from any 2 points is now going to be less than or equal to 2 times the maximum distance between that centralized point and any given point in space. So that's going to tell us that if you have this centralized point, then you're good to go. Well, how is that useful? Well, now we're going to use the contrapositive of that statement. We're going to use the fact that X is bounded. Well, then that means that for any point B inside of our space, there's going to be an element X sub n and X such that the distance from X to n to B is greater than n. And we're going to define K to be this value from the distance from X sub n and B. Now notice here that I can do this for any value of n, and what I'm doing there is constructing a sequence, X sub n, so that the distance from X sub n to B is greater than n. If I do something like this, I'm about to show that this sequence is very, very, very not Cauchy. Let's show how that would work. Let's see the distance from n plus k to n here. Then I'm going to claim that the distance between these two things is going to be very large. And the way I'll do that is try and compare what both of these things are in terms of the value of b. So let's go through and see how that sort of thing looks. What we're going to get is that this value here is going to be greater than the value of n plus k away from this function, and that this value right here. So instead of trying to find distances between corresponding elements of 2 different sequences, we want to try and see if we can boil things down to just one sequence. Now, this ends up being a little bit unwieldy itself and trying to get from 2 sequences down to 1. What we're going to attempt to do, essentially, in this proof that's to come, is we're going to say, okay, we're going to create a point in a sequence, and we want our second point to be farther away from any other point that came before it in the sequence. If I'm able to continue to say, okay, this point is not only far enough away from the previous point in the sequence, but any points that came before it in the sequence, then I'm able to say, okay, no subsequence here can be convergent at all because there's no way that you can get a Cauchy subsequence out of that. This is very nice in the natural numbers because you can just go 1, 2, 3, so on and so forth. But with an arbitrary metric space, it ends up being a little bit trickier. And that becomes a little bit of the kind of the weird essence of this part of this lemma. So to do this, we're going to define the distance from a set for a point X to be the distance from that point to the set A. That is the infimum of all possible distances between points inside of the set and the point x. The infimum, because this could be an infinite set, although for what we're going to need it for, we're going to be looking at finite sets. So first, we're going to show the following statement. If there exists a finite subset A subset of x and a value m in the real numbers such that the distance from x to A is less than or equal to m for all x and x, then x is bounded. Let's talk a little bit about this set. We're saying that there is a space x and that there's some finite subset somewhere, so that every other point inside of the set is at least some distance, and a bounded distance, in fact, away from that point. So, for example, the farthest this point can go, the farthest this point can go, farthest this point can go. The largest that possibly is less than or equal to some finite value. Well, it kind of makes sense how you might go through and do that, right? And this is essentially this first paragraph of the proof. You might say, okay, this is close enough to some point here in this set, and maybe the point over here that this point is closest to this point. So I could just start measuring distances between those 2 points. And then so distance from the first point to the set, then the set to the next point in that set, and then finally to the second point that I want to try and measure the distance to. But the distance there is going to be bounded by my traveling over there between each of those pairs of points. And that's exactly how I get to end up knowing that this space x is bounded whenever there's a finite set such that everything was in a finite distance of that set. Now let's assume that x is unbounded so that the contrapositive of this statement is true. So x is now unbounded, which means I get to now negate this first part of this sentence. Now, for any finite set that I choose and any value of m, there's going to exist a point in the space x such that the distance from x to that set A is greater than m. Now, what I'm going to need is just m equals 1. So I'm going to say that for what is to here on out. Let's fix a point x1, just any arbitrary point inside of our space. And let's pick x2 so that the distance from x2 to the set containing x1 is greater than this value 1, or m, as we've been writing it. Notice that I can do this by exactly this contrapositive. I have a finite set and I have a value, so there's going to exist a point x that makes this distance true. But notice that I can do that at any point of this recursive process. After having chosen x1 to xn plus n minus 1, I can then choose xn so that the distance there between xn and any other point in that set is going to be greater than 1. So that's going to mean no subsequence of x of n can be Cauchy. Indeed, if I try and choose any 2 distance between points, the distance from xm to xn is going to be greater than or equal to the distance from xm to x1 to xm minus 1, and that's going to be greater than 1. So the distance between any 2 points that I choose is going to be greater than 1. That means I cannot choose a convergent subsequence out of this. So note that this one becomes a little unwieldy in its nature, even though it's rather maybe a well understood or visually type of proof, because I have to start thinking about, okay, it's not the natural numbers where everything is in one line. I have to start thinking about how maybe I could go about and say, maybe I'm going far enough away whenever I make little jumps going from 1, 2, 3, and 4, but then maybe I end up back at the same point. And if I continue that sort of process, just going around through these 2 points, it's not enough just to say that the next point in the sequence is 1 away from the previous point. I need to be able to say that it's 1 away from any other point inside of that sequence. Essentially, I'm using that unbounded nature of the set X in order to do that. So the corollary or proposition that comes from that is that every compact set K in a metric space is closed and it is bounded. We've adapted everything else in that one direction of this proof because we got rid of that diverges to infinity notion. So we can now say compact sets in a metric space are closed and bounded. We would love to be able to say the opposite, but it turns out that the opposite is not true. The space of the natural numbers with the discrete metric is a closed and bounded set. Note it's bounded because with respect to the discrete metric, the highest distance between any 2 points is 1. It's a complete space as well, in case that wasn't useful to us, and it's, of course, going to be closed. Well, maybe it's closed because what? We have any convergent sequence is the same as a Cauchy sequence inside of the relative metric there. So we know that the reason for it to be closed is that any point that is a limit point of a sequence inside of this set is going to be eventually constant. And so that point would have to be inside of the set. However, The sequence 1, 2, 3, and so on does not have a convergent subsequence in the discrete metric. The distance between any point and any other point in the sequence is going to be 1. So there's no convergent subsequence here. So notice that closed and bounded is generally not enough to show that a metric space is compact. So this case, for example, closed and bounded, we combined those together, but it did not give us a place where every sequence had a convergent subsequence. So we need to strengthen boundedness a little bit to get to that point. So what are we going to do? We need something a little bit stronger on the bounded, it seems like, because the natural numbers, it seems, you can get bound between any 2 points, but then somehow in our head, right, we're still seeing that you can go off into so many different directions with those points that you're not able to really get to everywhere that you would like to be. So let's use a different definition here in terms of totally bounded. And the reason that we're going to use this is that now we're going to be able to say for each epsilon greater than 0, that there's some finite number of epsilon, balls of radius epsilon centered at specific points inside of our set that cover the entire space. When I say cover here, I mean that you could take a union of each of these sets, union these as I goes from 1 to n, and say that that's equal to the entire space X. This would mean that the set of all of these balls cover the set X. So the union is equal to them. And typically it's okay if even this is a containment relationship, if the union of the balls contain X. But because these balls are contained within X, this is just good enough for us here. Actually, no, that's not. So here we get to say this instead, because I forgot that this is actually a subset A that we're saying instead of the metric space X. So the balls here are going to cover A, which means that the union of these balls will contain the set A. There we go. Now that they cover A. Picture-wise, what does this look like? It looks like this. Here you've got your subset A maybe in the metric space, which is this entire page. And you can see here that there are various balls of the same radius that are covering this space. Same thing over here. You can see here that each of these balls is covering the space and the radii have shrunk. So maybe your balls move where their centers are, and maybe that moves how many there are as well. But the thing is that there exists, for any radius that you choose, there exists finitely many of these balls that will cover our entire set. So an example here is the open interval from 0 to 1. This is a totally bounded set, because for any epsilon that you might choose, you can find balls that cover 0, 1, right? If you just are looking at the interval going from 0 to 1, then you can start saying, okay, whatever my epsilon is, I'm just going to basically have them all link up with each other, and eventually I'm going to have that my open sets cover my entire space. They can be a little bit larger than 0, 1, and that's okay. The union of them have to contain the set 0, 1. However, the natural numbers with the discrete metric is not a totally bounded space. This one is not totally bounded. And that's because if epsilon equals to 1/2, we always come back to this example, right? It's not totally bounded because if epsilon equals 1/2, then the balls of radius epsilon around any natural number is just the set containing n, because there's no larger distance that you could take. The only distances are 0 and 1, and so because nothing is of distance 1 away inside of this ball, it's only of distance 0, and it's going to be the point n itself. And then there is no way to take a finite union of these balls and cover up all of the natural numbers, right? So the picture there is, if you try and take that to make it the natural numbers here, so here's 1, 2, 3, 4, 5, 6, then your epsilon balls, you need infinitely many of them in order to be able to make these cover and make these work. This is kind of a picture more in the relative metric, but you can imagine how this works in the discrete metric by our kind of pictures that we've worked with there. The neat thing is that compact spaces in metric spaces are this notion of totally bounded. So in fact, not only are they closed and bounded, it turns out that they're totally bounded as well. So we'll show this by taking a set here which is not totally bounded and show that it is indeed not compact. Remember, not totally bounded is going to mean that we can find some sort of epsilon, some radius here for our balls so that it takes infinitely many of them regardless of how we arrange them. So let's go ahead and show that we can then get a sequence that does not have a convergent subsequence here. Let's see if we can do it. Let's take x of 1 to be inside of this set K. Then the ball of centered at x1 of radius epsilon, that is this epsilon so that it takes infinitely many balls to cover K, does not cover K because it is finitely many balls. So we can pick some sort of x2 that is outside of this ball entirely. We can now continue inductively and find a value of x sub n, which is in this space K, but not inside of this union. Then it turns out that for any n that is not equal to m, since x sub n is not in, it's not within the union of the balls of radius epsilon around any particular point. In particular, it's not in the ball of x sub n, x sub m of radius epsilon. That means that x sub n and x sub n have to be different in outside of each other's epsilon balls. So xn is not within epsilon distance of x sub m, and that's exactly what this means. I should have written d here for this, and so that distance is greater than or equal to epsilon, and so for exactly the same reason as our previous proof, we cannot have a Cauchy subsequence, and hence we can get no convergent subsequence here. So the contrapositive gives us what we want. Any compact set must be totally bounded. So maybe this characterization helps us with trying to figure out what compact sets look like. If already we know that compact sets are totally bounded, we just need to be able to show the reverse. Namely, if you have a set that is closed and totally bounded, then perhaps we can say that it is compact. And that's exactly what we get to say. First, note that totally bounded, a set being A being totally bounded, that this implies the fact that A is bounded. And I'll leave that to you to go through and see how that works. Try working through each definition here to see that if A is totally bounded, then A is going to be bounded in terms of the two definitions here, so that the notion of totally makes a little bit of sense here. But this gets us here near to the end of what we're going to be discussing as we start finishing up talking about these compact spaces and how we characterize them in metric spaces. We'll get to this kind of big main theorem here, which says that a subset of a complete metric space X is compact if and only if it is closed and totally bounded. Notice that we do add the completeness here. We're going to ask for complete because this is going to be nice for us to say things are closed, right? If you have something that is a limit point, then maybe that limit point, you want it to be just that of a Cauchy sequence. So adding complete here makes things a lot easier in terms of how we would write this proof, because we can now construct Cauchy sequences and use that to get some sort of convergent point. Basically, it says that Cauchy subsequences would be convergent subsequences, which is something we need for compactness. So let's see this here in this proof. We only need to show that a closed and totally bounded set is compact because we've done all of the rest of the stuff in the previous propositions. So let's take x of n to be a sequence in K. For each n, let's take a finite set of balls of radius 1 over n that cover K. So we're going to start by using this notion of totally bounded, which says that whenever you are taking a look at a radius of something like 1 over n, then you can always take a finite set of balls of wherever they're centered that cover K. Notice here, I'm not actually saying where these things are centered. I'm just saying that this is some sort of finite set of balls. Now, starting with n equals 1, let's pick a ball b sub I 1 that contains infinitely many terms of the sequence x sub n. Notice that there has to be at least one of these balls. The reason is a sequence has infinitely many terms in it, right? And so if we're, say, for example, double counting, then we're good to go, right? So this says that if you have finitely many balls of radius 1 over n, there's got to be one that has infinitely many terms of the sequence. If maybe perhaps you're thinking, oh, well, I don't want to double count if 2 points of the sequence end up being the same later on. There's infinitely many of those. I'm going to count those as 1 point. Well, if there's infinitely many things that all are equal to 1 point, then you have your convergent subsequence already. So let's assume without loss of generality that we're able to spread around our points a little bit, put some over here, put some over there, just put a little bit of dust. And that when we take a look at our sequence elements inside of our space of X, that whenever we cover it up with finitely many balls, that there's going to be some ball that has infinitely many terms of the sequence inside of it. Now, this ball inside here can be broken up into, well, it's going to be covered by circles of an even smaller radius. I can start now making circles of a radius 1/2, for example, and take a look at how these balls cover the space of what I've chosen. Now, notice here that I've picked a infinitely many terms of this, and I've called it B1. I can then say, okay, I'm going to take an element of that sequence and call that x of n1 to just be an element inside of that space of B1. Well, if I now take a look at the balls of radius 1/2, they're going to cover the entire space. Hence, they'll also cover this little ball that I have inside of here, which gives me my little subsequence. So then what I'm going to do is pick one of those little 1/2 radius balls that contains infinitely many terms of the sequence, and for those that live inside of the space B sub 1. There should be, again, infinitely many terms of this sequence because we're able to break this apart into finitely many balls in terms of their intersections. And so one of the intersections of the space B1 intersect with B2 for some I has to have infinitely many terms of the sequence xn. And again, the reason is if for all I, B sub 1 intersected B2I has finitely many terms, then since the union over I of these n B1 intersect B2I is equal to B1, because this covers the entire space X, it also covers the B1. So since that is equal to B1, then B1 had finitely many terms of the sequence, which would be a contradiction for us. Finitely many terms of this sequence, which would be a contradiction. So that's what we're using. We're using the fact that there has to be at least one circle here, radius 1/2, has infinitely many things that are inside of B1. Once we know that, we can then choose an x of n2 that's going to be inside of B1 intersected with that B2. And that's exactly the recursive process that we're taking. We start with an x of 1 inside of the element B1, and we continue to recursively pick x of nk such that it is within the intersection of all of these b sub I, and such that you're able to pick one such that its index is a little bit larger than the previous one. So we note that here that any time that you pick two values of your subsequence, that they're going to be inside of the cutoff, the b sub n, where n is the cutoff point that you have those 2 points of your subsequence passed. So the distance between them can only be as large as 2 over n. The diameter of a ball of radius 1 over n is going to be 2 over n. That means that this x of nk is a Cauchy sequence. Since x is complete and k is closed, the subsequence must converge to a point inside of k. So totally bounded is what we needed here. That was the connecting piece. Bounded was not enough because we found that there are examples of closed and bounded sets that were not compact. It works in the real numbers, but not with metric spaces. So we saw that we needed to add this notion of totally bounded to make that theorem work. Looking at how we can connect this sort of world that we're looking at with some of the other concepts that we've been doing throughout this past week. One little neat proposition that I want you to think about and try and get a proof for is this one. Every compact metric space is complete. Notice in the thing that we said above that we can characterize complete spaces in terms of that they are compact if and only if closed and totally bounded, and that was neat for our proof. But it turns out that every compact metric space is already complete, helping us with one of those directions for that proof. I want you to think about where that comes from. Use definitions of compactness and completeness to try and help you prove this proposition. Another neat thing is that a closed subset of a compact set is also compact. Think if you take sequences x of n inside of f, then there is going to be an inclusion argument that allows you to say the x of n is inside of the larger set k. So hence there's going to be some subsequence. These x of nk also live inside of f. So they converge to a point x that is also in f since it is closed. And that's going to give us that f is compact. Now, how do continuous functions work here with compact sets? Remember from the extreme value theorem that a continuous function f attains its maximum and a minimum inside of a contact interval whenever we take a look in terms of the real numbers. If we combine this with the intermediate value theorem, we deduce that f hits not only that maximum and minimum, but every y value in between. So if we look at f of x1 comma x2, we get another compact interval, y1, y2. Notice that this also happens in terms of metric spaces. That is, if fx going to y is a continuous function between metric spaces, then the image of a compact set is also going to be a compact set. So like in terms of the reals, we saw that compact intervals map to compact intervals. This is a very much a similar sort of notion. We're not trying to say anything about intermediate value theorem here yet, but this proposition does say that there's maybe some sort of hope to something similar to that direction. That is that if you start with a compact set and look at its image through a continuous function, then what you get is going to be compact. Well, to show that f of k is going to be compact, we need to start with a sequence in f of k and then show that that sequence has a subsequent, a convergent subsequence. So let's take y sub n to be a sequence in f of k, and then let's define a kind of a corresponding function with it back in the domain. Since each y sub n is the image of a point inside of a set k, then I can let x sub n be f inverse y sub n be the corresponding sequence inside of k. Well, this sequence x sub n is in k, and since k is compact, this subsequence is going to converge to some point inside of the space k. Since f is continuous, f of x sub n k converges to f of x in f of k, and this is exactly the subsequence that we were looking for. And that's because this is y sub n k, converging to the value f of x, where x is the limit of the convergent subsequence guaranteed in the domain sequence. That's a neat little correspondence that helps us connect notions of extreme and intermediate value theorem from the real numbers and helps us out with this proposition here. We'll see a lot of these propositions come up as we prove things because, again, compactness is something important to us. We want to really characterize it because it is this notion of topological finiteness. It guarantees us a lot of very neat and slick formulas, as we'll see here with the extreme value theorem. If we assume that K is a non-empty compact subset of a metric space, and that F is from that compact subset to the real numbers is continuous, then F has an absolute maximum and minimum, and both of those are contained within the compact set K. The proof of this is really straightforward now that we've proven all that we've done, and this is an example of that slickness. The reason that we prove some of these maybe more in like kind of out there kinds of theorems and lemmas and propositions is that it helps make these buildups so neat and unique. It makes it so that these are just kind of connecting building blocks to get us to some of the big theorems that took us a while to prove before. Let's see it here. The codomain of f is the real number, so since f of k is compact, it contains its supremum and infimum. That comes from the extreme value theorem on the real numbers. Because, well, rather, it comes from the fact that from the definition of compact on R is what I should say. And the reason is this comes from the definition of compact. Any compact set is going to be closed and bounded, so it has to contain its supremum and infimum. Those are two values that it has. It's bounded, so it's got a supremum and it's got an infimum, and then it's closed, so it's going to contain those 2 points. Hence, there are x values in k that map to the supremum and infimum by the definition of f of k being the image. And that's it. And that's good enough to go. A really neat and slick proof, a blink and you miss it sort of thing, that once you've gotten this notion of compactness down and you know where things are looking for, a lot of these sorts of theorems can start chalking themselves up to this boiling down to things that we've already done in terms of the real numbers, which is a really beautiful thing to get to that point. It means that we've kind of started looking around and seeing that we've proven the main things that are helpful to us in the future, to see that functions on compact sets do have maximum and minimum whenever they are mapping into the real numbers. But that'll do it for us today. We've talked a lot about this new concept of compactness here. We've first characterized compactness in terms of the real numbers. That is, that these compact sets were closed and bounded. You may have been familiar with this notion from Heine-Borel. And then we said that in terms of metric spaces, we have to do a little something more. We have to add a little sauce. We have to add this notion of totally bounded to our sets. So we've gotten through what is, I think, the biggest thing from this set is noticing how topological arguments work, how very set focused they are. some of them definitely are going to relate back to distances, like in metrics, and we're going to be using that as an asset as we go through these arguments. But a lot of our proofs end up looking a lot like this one whenever we're trying to do some theorems with regards to compactness, using this notion of totally bounded in terms of finitely many balls of a certain radius covering a set. So looking over these sorts of proofs and knowing how this progresses from beginning to end, how we are constructing the balls that we're looking at and how that gets us a sequence later on is a very neat connection and something I recommend taking a look at at some depth there. But that'll do it for me today. Thank you so much. Have a wonderful day.